Let's take a step back and think about the structure of a data set. There are three parts. Data sets are collections of values, typically numbers or strings. These values are organized by variables and observations. A variable contains all the values that measure a certain attribute across units. An observation contains all the values that are measured on a unit across attributes. What we want is to have all the variables as columns and all the observations as rows, leaving every cell to contain a single value. In data management, we can further split variables into two types. Fixed variables are those variables that we know and can define in advance, while measured variables are what we actually measure in the study. How we arrange these things varies with the data we have and the questions we're asking. In this case, we're looking at vote outcomes for different electoral races in Tennessee. This means our measured variable is the vote count. Voting procedures are organized geographically, so our unit of observation is at the precinct level and for a particular set of races. Note that the geographic nature of voting can be a bit confusing because we have multiple options for geographic level. The smallest unit we have is the precinct, so we'll use that for our rows. But later, we'll look at how we might roll this up to the county level. And of course, actual voting outcomes are measured at the district level. For statewide races like president, U.S. Senate, and governor, the district is the whole state. But for U.S. House and Tennessee General Assembly races, the district is a geographic unit that can be as small as a part of a county to as large as several counties. And sometimes it even divides counties. Further, while they are standard for a given race and election cycle, they do not evenly nest within each other. In this case, we want a data set that has the following variable columns. We need some geography columns, which should include a vector for county and for unique voting precinct. We need a vector for office and for its associated district. We need to know where the votes went, and that can include some combination of candidate and/or party. And then we need to know how many votes there were, or the vote counts. This means that each row should show a precinct's identification, its county, the office of a given race, the district for that race, the candidate or party, and the votes that went to that candidate in that specific race at that particular precinct. The good news is, it's only the candidate and party information that needs adjusting here. Let's start with the easiest things that need fixing. The first thing that we should probably take care of is DeKalb County. DeKalb County is listed twice in this object with a slightly different spelling. Once with a lowercase k and once with an uppercase K. And since R is case sensitive, we need to unify that. For simplicity, I'm going with the uppercase K approach, but I suppose it doesn't really matter too much. And we do that by taking our TN 2020 object and piping it into a mutate, where county equals if else, county, if it is equal to DeKalb with a lowercase, should become DeKalb with an uppercase. Otherwise, store back into it whatever is currently in county. We also need to make some minor adjustments to the geographic identification variables. Right now, we have a variable for county and two variables really, for precinct, but we can't just use the precinct variable, either one of them, because sometimes the names are the same across counties. So what we're going to do is we're going to create a unique ID variable by combining these things together. This is the next mutate line. Mutate for a variable ID that we're going to create. And we're going to use this command called paste, which takes two string material items and puts them together. It pastes them into one. And we are going to paste county and the precinct sequence into one variable. We'll still keep county and precinct by its different names, of course. But we are going to, in the next line down, rename a few things, including county, because who wants to have to type capital letters all the time? So we will rename county, and we will also rename these ball-seek ID and juris ID variables into something a little more intuitively obvious. We know that they are office and district, respectively, so we'll call them office and district. Then, because we know that office is a factor, it contains a discrete finite set of labels, and we don't have to want to remember what the 3 and the 7 and the 11 are. We're going to do one last mutate here before we close out this particular code block, where we are going to make office a factor, using the values that are in office, but setting the labels for the numbers in order accordingly. Let's run that. This next step is optional. It doesn't really matter too much if you do it or not, but I kind of like to trim things down and get rid of things we don't need, just so they're not cluttering up my mental space, if nothing else. So we're going to do that by piping the Tennessee 2020 object into a select, where we're going to put a minus sign in front of every variable that we don't want to keep. And then we're going to finish this off by putting the ID column that we just created at the very front by using another select and telling it to select ID and then everything else. And then we're just going to go ahead and store that as a tibble, which don't worry too much about what that is. It's a particular data file format. All right, now let's make the data tidy. Normally, we might aim to pivot the table, but that's actually not possible here. And I tried this before recording this video several times before realizing that was the case. The reason is that the candidate, party, and vote information are all contained in 3 recurring sets of columns. What we need to do is stack all of those sets into a singular column set. So what we're going to do instead is we're going to write a function to pull the metadata plus a single voting information column set. And then we're going to run that through a loop to stack those sets together. Now that was a lot at once, so let me walk through what's happening. We're going to create a function that I am calling extract votes, and it has one variable in it, I. And our function does something very simple. It takes the 2020 Tennessee data object and it pipes it first into a mutate, where we are going to extract the candidate, party, and vote vectors into vectors that are named candidate, party, and votes. And we do that because the names are what we're having to reference. And there is a way to reference names inside of a mutate and some other helper verbs, but you can't do that inside of a select. And we're going to need a select ultimately to extract our variables of metadata, the ID, county, precinct, office, and district, as well as our candidate, party, and vote information. So the way this works is we're using a set of nested commands that I showed you briefly previously, the eval, parse, paste combination. And what we are doing is we're taking the beginning of each variable name, our name, and pasting it, this time a paste 0 so there's no space, with whatever I is. And we're putting that into each of these for candidate, party, and votes. Once we create that function, we can drop that function into a loop. And what we're going to do with this loop is we're going to iteratively extract the needed material, bind it onto a separate object that we'll temporarily make called clean data, and then restore clean data. And what it will do is it will run through this loop as long as I goes from 1 to 10. So we start by saying make clean data null, because we have to put it into memory somewhere, and then we run the loop. And it takes only a second for R to do this. Now, before we go any further, we have a little bit of cleaning up to do and a few things that we should probably check. 2 of the most important things are going to have to do with the votes column and the party column. So we're definitely going to be getting rid of any rows that have no value for votes. those simply came from the fact that there would have been places far out in that original spreadsheet where there were no candidates, not even write-ins, and so there just was nothing to put there. So we're going to filter those out. But then what we also found earlier is that party affiliation is only listed for Democrats, Republicans, and Independents. If a write-in candidate was listed, there is no party affiliation. And so for simplicity, we'll just go ahead and give them their own party of write-in. I guess they're the write-in party. But we need to make sure that everything came through correctly before we go further. So that's what this block of code does. We're going to take that clean data object we just made. We're going to filter it to go ahead and get rid of all of the non-existing votes. And then we're going to look for just the places that are left where the party variable is also missing, is in A. Then we're going to group by candidate and tally it and make sure that we can actually do what we want to do later. And it looks like, yes, we can. In every place, after we get rid of the missing vote rows, where party is also missing, the candidate has the word write-in at their front. We can use that to our advantage. So let's come down here and do some final cleanup on our object. So we're going to take clean data and we're going to store it back into TN 2020, overwriting what's there. But before we do that, we're going to pipe that through a filter command where we're going to get rid of all of those rows with missing values for votes. And then we're going to pipe that into a mutate where we're going to update party using this if-else statement. Our logical expression that needs evaluation is one that I've not shown to you yet, and I'm not going to worry too much about it. It is a way of looking for patterns, text patterns within a variable. So we're going to look for the pattern write-in in the variable candidate. If it's found, we're going to make party write-in. And if not, we're going to leave it as party. So let's run that, and then we'll clean up the workspace a bit, getting rid of some objects that we don't need anymore. And then it's always a good idea to go ahead and save your data object. We are now ready to turn to answering our questions. What were the electoral outcomes for all races in Tennessee in a given year? Let's start by pulling a table of the winning party for each race and their share of the vote. We're going to use this block of code to do that. We'll start by piping our object into a group by where we are going to group by office, district, and party. Then we're going to put that into a summarize command. We're going to summarize votes is equal to the sum of all votes, but organized by office, district, and party. Then we'll ungroup that and regroup it by just office and district. And then we're going to put on a mutate where we're going to do % equals votes divided by the sum of votes times 100. And then we can identify the winner. Whoever had more than 50% of the vote must have been the winner, and they get flagged with a 1. And then we'll filter out those who are the winners and give ourselves a full table. Let's see what we end up with. So, this is just the top portion. This doesn't yet show the state legislature. We'll get to that in a little bit here. The top of this table actually gives us our first hint that there might be some gerrymandering going on in Tennessee. The two statewide races saw the Republican candidates win with around 60 to 62% of the vote. We see much higher rates in terms of winning in the U.S. House races. The lowest value we see across any U.S. House race is 66.7%. In many cases, we are in the upper 60s to the mid 70s, and even House District 5, where one candidate got 100% of the vote. This suggests there may be some packing and cracking going on in our district layout. Let's turn to question 2 to explore this a little bit further. How closely do electoral outcomes match voter preferences? In an ideal democracy, the proportion of votes should more or less match the proportion of seats that a party wins. When measured at the district level, this is what happens. Whoever has a majority of the votes wins. But when measured at the aggregate, do these proportions still align? Well, let's take the votes statewide by party for a given race, irrespective of district. Now, one hiccup in this process is what we saw a moment ago. District 5 for the U.S. House, the reason one person won 100% of the vote is because only one person was on the ballot. So we need to deal with uncompetitive races, because uncompetitive races by default don't really show us the will of the voters. There isn't actually a choice. So before we can do this, we need to flag races where only one candidate appeared on the ballot. That happens in this block of code. And we're going to be adding a new variable and making some changes here. So let me walk through how this happens, because there's a lot of parts here. We're going to take our voting object and again pipe it into a group by for office, district, and party. And again sum up our votes and again ungroup. If we ran this as is, we would get a very long table where we would have office and district and a party and a total of votes that they got. When we add this next line and we pivot wider, what we're going to do is we're going to take that party vote set of vectors and we're going to flip it so that now the party names run across the top and the total votes are in all of the cells. See how we did that? Now we can identify an uncompetitive race. We can add a mutate where we put a new column at the end here that we're going to call uncompetitive. And we're going to give it a 1 for a certain set of conditions to flag it as uncompetitive, or a 0 if it doesn't meet them. The conditions are not complicated, but there are a lot of parts. If we look closely at the columns down here, particularly let's start with U.S. House 5, we can see that there was one Democratic candidate, there were no independent and no Republican candidates on the ballot, and 14 votes went to some write-in candidate. It was actually 2 candidates, I checked. And if we were to continue to scroll down through other races that are at the state level, we would find many more that follow this pattern, where there would usually be a Democratic candidate and no others, or a Republican candidate and no others. But occasionally there's a Democratic candidate without the converse, or vice versa, but there's an independent candidate who made it onto the ballot. I don't know details on that. We'd have to do a little bit of digging to find that out. But that means that what we need to look for is a case where basically only one of those 3 has a value. And we do that through this conditional statement. In the first part, we're going to say if the Democratic column and the independent column are both missing, then it's going to be an uncompetitive race where there was only a Republican candidate. Or, if both the Republican and independent columns are missing, then there was a Democratic candidate and no others. Either way, it's an uncompetitive race, and so we mark it as such. Let's see what happens when we run that. See? Now we have a column for uncompetitive. Now, to simplify this back down, we're going to select just office, district, and the uncompetitive vector, because that's really what we need to know. Where were the uncompetitive races? And then we're going to join that back onto the original object. The left join is one that we may not use a whole lot, and I'm not going to go into much detail, but just so you know how it works. It's a way of taking 2 data objects and matching them up with each other by some set of vectors. So what we're going to do is a left join, where on the left side is our original data object, which is still in memory at the moment. On the right side, the Y, is everything that we're piping in, and we're going to join it by office and district. And when we do that, we get a complete data set where now we have added on that uncompetitive variable to everything else in there. So let's run this whole thing. Our object is now updated. If you're following along, we now have 66,142 observations of 9 variables. Now let's remove the uncompetitive races and total the votes for an office statewide. We can take our now updated object and pipe it into a filter where we say uncompetitive has to not equal 1. We could have also said uncompetitive is equal to 0. Either one works. Then we will group by office and party, do a summarize where we total up the votes by office and party, ungroup and regroup by office, and then put in a mutate where we look for the percentage of votes. Then get rid of the votes column itself, because all we really need is percent in the end. We're going to do another pivot wider to be able to get it into a nice human-readable format. And here is what we end up with. So among competitive races, we see that Republicans generally win about 2/3 of the vote, and Democrats generally win about 1/3 of the vote. If the awarding of seats was proportionate to the vote tallies statewide, then we would see that for the Tennessee delegation to the U.S. House, 6 of 9 seats went to Republicans and 3 went to Democrats. We would see that the Tennessee House of Representatives, which has 99 seats, would have gone 64 seats to Republicans, 31 to Democrats, and 4 to independents. And we would see that for the Tennessee Senate, which has 33 seats total, but only half of them are on the ballot in any given year, and this last time around it was 16 seats that were on the ballot. If the vote proportionately actually awarded seats, then what we would see is 11 of those 16 seats going to Republicans, 4 to Democrats, and 1 to independents. So how does that compare to actual seats won? We can do another data object, really an output, where we take our main data source, we pipe it into a group by again by office, district, and party, summarize the votes, ungroup it, regroup it by office and district, do our mutate to get our percentage, assign our winners, ungroup it again, and then filter out the winners. We've done a version of this already. But now we're going to group it by office and party, total it up so we see how many winners there are ultimately by office and party alone, and pivot that out to put party across the top. And here's what we see. No surprise on President and Senate. It's a statewide race effectively, so there is only 1 seat per se. But for the U.S. House, we see that 7 out of 9 seats went to Republicans instead of the 6 we might have predicted from the vote totals, and only 2 to Democrats. Instead of a 67 to 33 split, this is a 78 to 22 split. The Tennessee House is almost as skewed. 73 seats went to Republicans and 26 to Democrats. But we predicted, based on the vote totals, it should have been 64 to Republicans, 31 to Democrats, and 4 to independents. Notice that no independents won in the Tennessee House. And the Tennessee Senate shows something similar. 14 seats went to Republicans instead of the 11 we would have predicted, 2 to Democrats instead of the 4 we would have predicted, and none to independents, when it looked like 1 independent should have won a seat. The conceptual portion of your midterm exam will ask you to replicate this process for a different election year. And if anyone is interested in electoral outcomes, aggregating data from several years would allow for some very fascinating analysis. Who knows what interesting things you might discover?